Okay, so this video is on section 5.2, where we're going to talk about the sine and cosine functions and also what the parent function looks like. So we're going to sort of graph what it would be, and that we're going to see that it is going to be a periodic function. So as a review, in a warm-up, we're given a graph of a function here, and we're going to determine what the amplitude, period, and equation of axes for this periodic function is. So to me, the easiest thing to get the amplitude and the equation of axes is always find out what the peak value is. So it gives the peak value as the highest value. In this case, it hits the peak several times. So the peak value there is 2. What's the trough? So the trough is -1. So our equations for the amplitude is going to peak plus trough over 2. Sorry, peak minus trough over 2, which is 2 minus a -1 over 2, which is 3 over 2, or a 1 and 1/2. And the equation of axes is peak plus trough. So the two equations are very similar, so try not to mix that up. Again, equation of axes, you can think of it as sort of the average of the maximum minimum, so that's why it's peak plus trough over 2. In this case, it's going to be 2 plus a -1 over 2, which is 1/2. So we could sort of verify our answer by drawing the equation of axes on our graph. So that's roughly 1/2. And again, the definition of the amplitude is really the distance between between our equation of axes and the peak, and that is 1 and 1/2 over here, and it's going to be the exact same distance from our equation of axes to the trough, and that is also 1 and 1/2. The last thing the question asks for is the period, so that is the length of one cycle, and again, a cycle is when the subpattern starts repeating itself, or what's one part of the graph where the pattern starts repeating. So we can identify a cycle in this graph in several ways. One technique I like to do is either going from peak to peak or trough to trough. This one's a little bit tricky because, for example, in this part here, the peak repeats itself. In other words, it's staying at its value of 2, but that isn't necessarily the cycle. So what we want to do here is, let's look at this. Where sort of the peak, it hits the peak and it stays at the peak. Where else is that going to repeat in our graph? Well, that's also right here. So here we could define that to be one cycle. And the length of this cycle is 1, 2, 3, 4, 5. So the period is 5. Okay. So let's go to our lesson for today. So really what we want to be able to do is just look at what sine of theta is and cos of theta. So back in Unit 4, we did a lot of trig ratios based on sine and cosine. And what we're actually going to see that it is a function that we could graph it. And then once we've graphed it, let's look at some of the properties of it. So with any function that we're given, if we're not sure how it looks like, we'll always come up with a table of values. So here I come up sort of like a horizontal version of the table of values. So this is going to help, we're going to have to be reminded of exactly what the exact ratios are for these angles. So I purposely chose 0, 30, 60, 90, 120, so going by increments of 30 degrees. And these will come up to some exact values. Although for the intents and purpose of graphing though, we're just going to want a decimal value in there so that we can actually plot roughly where it is. So let's go through this. So let's assign a 0. So maybe on the side, a little review of what the exact values are for sine. So sine of 0 was 0. Sine of 30 was 1/2. Sine of 60 was √3 over 2. And sine of 90 was 1. So let's go and start filling in this table. So sine of 0 is 0. Sine of 30 is 1/2. Sine of 60 is root 3 over 2. Sine of 90 is 1. So now when we get past the 90 degrees, this is why I provided a reference grid for us so that we could sort of go back to our basic trigonometry and get the exact value of our degrees that are greater than 90. So here we're looking at 120. 120 might look something like that. And again, our reference angle here is going to be 60. So sine of 120 is really the same thing as sine of 60, which is going to be root 3 over 2. Likewise, sine of 150 is going to be the same thing as sine of 30, which is 1/2. Sine of 180, so sine again is y over r. So in this case, at 180, y is 0, so sine of 180 is going to be back down to 0. So once we get into the third quadrant, which is over here, so in the first example, or sorry, in the next value of 210, so that would be 210 over here. Our reference angle here is going to be 30, but remembering our cast rule, in the third quadrant, sine is negative. So really sine of 210 is the same thing as negative sine of 30, which is going to be negative 1/2. Sine of 240, therefore, is going to be the same as the negative sine of root 3 over 2. Negative sine of 60, which is root 3 over 2. Sine of 270, so over here, this is going to be y over r, and we're going to see that the value of y is actually going to be negative r. So sine of negative 270 was actually negative 1. Once we get to the third quadrant, so over here, 300, so here alpha would be 60. So in the fourth quadrant, sine is negative. So sine of 300 is the same thing as negative sine of 60, which is negative root 3 over 2. Sine of 330 is the same as negative sine of 30, which is negative 1/2. And once we get back to 360, well, that's the same thing as sine of 0, which is 0. So like I said, for the intensive purpose of our graph, let's convert root 3 over 2 to a decimal, and that's roughly around 0.87 or 0.9. So that's going to be negative 0.87 and negative 0.87. So let's go off and plot these, and hopefully as we're filling in the table, you're recognizing that there was a repetition of the y values, that there seemed to be a pattern there. Once we graph it, the pattern will be a little bit more obvious to us. So here we got 0, 0, 30, 1/2, so there's a half roughly right there, 60 and 0.8. So roughly around almost like 0.9, so maybe right there. And at 90 we hit 1. And then 120 we hit again 0.87. And then at 150 we're going to hit 1/2. And then 180 we're going to hit 0. Okay, so now we're at 210. 210 is going to be negative 1/2. Make it a little bit smaller so I can see the values as I plot them. So 210 and negative 1/2 would be right there. 240 and negative 0.87 or almost 0.9 might be right around there. And then finally at 270 we get negative 1. At 300 we get negative 0.87 again. 330 we get negative 1/2. And at 360 we get 0. Okay, and if we would continue this pattern, so let me say if we continue this pattern and get 390 degrees, well, that's the same thing. Sine of 390 is the same thing as sine of 30, which we saw that was 1/2. And notice that here, that numbers are going to start repeating. So we do see that the sine curve or sine function is a periodic function, and it's going to repeat every 360 degrees. So we're going to connect the dots here with a nice smooth curve, nothing straight here. And let me try my best here to connect the dots. And there we go. So that's what the sine function looks like. It's a nice curve. People like to call it wavy. So it's sort of in the last unit, in the last section, I had an example that was a sinusoidal curve, and a lot of people describe it was like a wave, and that's exactly how I would describe it as well. So let's look at some of the characteristics. The period, again, I said was 360 degrees. Well, the equation of axes, let's look at that one first. Again, what's sort of the midway point? And here, another way we could look at it is our peak is 1, our trough is -1. So really our equation of axes is halfway in between. And that is really our x-axis, or y is equal to 0. The amplitude, well, the sine function that has a high value of 1, a low value of -1. And in our graph, it's kind of easy to see that the amplitude is 1. The range, so here the range is y is a real number such that it's between -1 and 1. So we see that the range or y values doesn't go above 1 and it doesn't go below -1. The roots, so where does it hit the x-intercept? So in this case, I kind of see I missed it on the graph there, but there are my roots right there. So the roots are 0, 180, and 360. So another way that we could express this is that the roots is 0 plus or minus 180 n, or n. Actually, we could just simplify that a little bit, not just plus or minus, but just make it plus, where n is an integer. So here, integer could be a positive or a negative. So here we see that the roots are going to happen every 180 degrees. Let's look at the cosine graph now. So let's kind of review what the exact values of the cosine for various degrees. So cos of 0 was 0, and my trick to my class was basically this was the opposite, going the other direction of sine. Sorry, the cos of 0 was 1, cos of 30 was root 3 over 2, cos of 60 was 1/2, and cos of 90 was 0. Okay, so let's go through the same thing like we did for the sine graph. So cos of 0 is 1, cos of 30 is root 3 over 2, cos of 60 is 1/2, cos of 0 is 90. So again, I put a little grid here for a reference. Hopefully by now that we could actually kind of visualize it and could do a little bit more quickly, but I'll use the grid here to sort of help us review this a bit. So cos of 120, so 120 is in the second quadrant. In this case, alpha, or the reference angle, would be 60. So we're going to see that the cos of 120 is really the same thing as cos of 60, but because using the cast reference, in the second quadrant, cos is actually negative. So this is really the same thing as negative cos of 60, which is going to be -1/2. So cos of 150 is going to be the same thing as the negative cos of 30, which is negative root 3 over 2. And finally, when we get cos of 180, so the definition of cos is x over r. In this case, x is going to be really the -r. So we get cos of 180 is -1. Finally, in the third quadrant, where we get cos of 210, so it will be somewhere in this quadrant. Again, in this quadrant, 210, the reference angle would be 30, and cos is negative. So cos of 210 would be the same as negative cos of 30, which is negative root 3 over 2. Cos of 240 would be negative cos of 30, sorry, negative cos of 60, which is -1/2. And at 270, because cos, to be by definition x over r, well, x is 0. So cos of 270 is 0. And once we get into the fourth quadrant now with 300 degrees, so there the reference angle there would be 60 degrees. So here we see that the cos of 300, and here cos in the fourth quadrant is positive. So cos of 300 is the same thing as cos of 60, which is 1/2. Cos of 330 would be the same thing as cos of 30, which is root 3 over 2. And cos of 360 is the same as cos of 0, which is 1. So again, we're going to see actually the same numbers that we saw with sine. They just kind of happen at different places on our x values. And before we graph this, let's convert root 3 over 2, just for my reference. That's 0.87. That's negative 0.87, negative 0.87, and this is 0.87. So let's graph what cos looks like. So here, we're starting at 0. Cos is 1. At 30, cos is roughly about 0.9, so maybe right there. And then we're going to see that cos of 60 is 1/2. Cos of 90 is 0. Cos of 120 is a negative 1/2. Cos of 150 is roughly negative 0.87, so right around there. Cos of 180 is negative 1. Cos of 210 is negative 0.87. Cos of 240 is negative 1/2. And cos of 270 is 0. Cos of 300 is the same as cos of 30, which is 1/2. Cos of 330 is the same as cos of 30, which is 0.87, so rough around there. And finally, cos of 360 is we're back up at 1. So we need to be careful in sort of connecting the dots here, because the maximum value of cos, in other words, the highest value you get for cos of any angle is 1. So these are the peaks, and we got to make sure that we're careful when we connect the dots, our graph doesn't go higher than that. So let's look at what cos of 390 would be, because that would be the next value here. Well, cos of 390 is the same thing as cos of 30. So that's going to bring us back down over here. And just for reference over here, cos of negative 30 is the same thing as cos of 330, which also is the same as cos of 30, which is 1/2. Sorry, 0.87. So here would be that point. So here you're going to carefully connect the points in a nice smooth curve. Oh, missed that one point over there. And it'll look something like that. Okay, so that's what the cosine graph or cosine function looks like. So how can we describe it, or what are the properties of it? The period, again, is also 360 degrees. The amplitude happens to be 1 as well. Our equation of axes is still our x-axis, because, well, cosine and sine have the same peak, which is 1, and then the same trough, which is negative 1. So really the amplitude and equation of axes doesn't change at all. Neither does our range. So the range is y is an element of the real number, such that y is in between negative 1 and 1. Now the roots for the cosine are a bit different. So we have one root at 90 degrees, and we have another root at 270, and we're going to recognize that the roots are going to be repeating as well, and they're going to happen every 180 degrees. But the difference here is it's going to start at 90 degrees, and here we could say that we can add any multiple or subtract any multiple of 180 to 90 degrees, and that's always going to be its roots. So in this case here, n is an integer as well. So how are the graphs of sine and cosine similar, and how are they different? Well, in a nutshell, they're the same. And really, the only difference is really if we shift, they're shifted left or right of one another. So they just sort of, so you can think of they start at different points. But here we could kind of see that if we shifted the sine curve this way, so that this peak falls over here, we're going to get the cosine graph. And likewise, if we have the cosine graph, and then we're going to shift, kind of hard to see, this graph will fall back down over here somewhere, that if we shift this to the right, we're going to get the sine curve. So really they're the same curve, same graph, except it's shifted either left or right. So here we're going to write that down. The difference is that one can be considered a horizontal shift of the other. Okay. So once we get to the rest of the unit and we're asked, or you're asked to graph a sinusoidal curve, you're not going to have to do all these points. Okay. In fact, we're going to remember 5 key points, and you only have to plot those 5 key points to get how our sinusoidal curve looks like. So let's first look at sine. And our 5 key points that we're going to look at is, well, when x is 0, 90, 180, 270, and 360. So here the exact values of sine of 0 is 0. Then sine moves up, or sine of 90 is going to be 1. Back down to sine of 180 is 0. Sine of 270 is negative 1. And sine of 360 is back to 0. So notice that the x values are broken up into sort of 4 equal parts, or 4 values that are exactly 90 degrees far apart. So in our graph, let's make 4 ticks that are roughly exactly exactly the same distance apart. And we're going to get used to this pattern. Hopefully you kind of remember it. Sine starts at the equation of axes, goes up to its peak, back down to, maybe it'd be easier if I do this in a different color. So again, sine starts at the equation of axes, goes up to the peak, back down to the equation of axes, down to the trough, back to the equation of axes. And maybe that's here, that's negative 1 and 1. Okay, so there's a distinct pattern when we're graphing for sine. Starts at the equation of axes, goes up to the peak, back down to the equation of axes, hits the trough, and back up to the equation of axes. So that's what we call the 5-point system in sort of graphing sinusoidal curve. So this is sine. We'll do the exact same thing with cos. So we look at cos. So if we look at cos, we have x, and what's cos of x? So we're going to look at the exact same x values of 0, 90, 180, 270, 360. So here cos of 0 is 1, cos of 90 is 0, cos of 180 is minus 1, cos of 270 is 0, and cos of 360 is 1. Okay, so we're going to have the exact same scale, or the same exact 4 intervals of our graph. And that's what we're going to eventually see as well, is that our sine and cosine curve are broken up into exactly 4 intervals. Why are we choosing 0, 90, 180, 270, 360? Well, it turns out if we look at our graph, and let me go back to our table of values after I do the scale here, is that those values hit our peak, our equation of axes, and our trough, equation of axes, peak. So that's where we're looking for when we graph it. We want to see the peaks and troughs and where it's also hitting at the equation of axes. And also the sine, same thing. Here we're going to start the equation of axes, go up to the peak, down to the equation of axes, down to the trough, back up to the peak. So we're choosing explicitly those 4 intervals where it's hitting those marks. So a quick sketch of a cos will look something like this. So let's say this is 1 and -1, and we'll always make a song out of it. We're going to start at the peak, down to the equation of axes, down to the trough, back to the equation of axes, back up to the peak. And so that's how our cosine works. So here, connect it. And notice that I'm very careful when I draw, especially with the cosine, when I start and end it, then do not go past the peak. Okay, so that's our lesson on how to draw the basic sine and cosine functions or the curves. And from the rest of the unit, we're going to actually look at transformations of that, but we're going to establish that pattern again with sine, equation of axes to the peak, to the equation of axes, down to the trough, to the equation of axes. Those are our 5 points. And for cosine, peak, equation of axes to the trough, to equation of axes, back up to the peak. Establish those patterns. We have to do that, and we'll do that over and over again in this unit.